Diabetes is a condition where the B cells in the pancreas fail to produce the hormone insulin, which causes excess buildup of glucose in the bloodstream, which can lead to clogged arteries, heart attacks, etc. Preterm birth is associated with an increased risk of diabetes because of underdeveloped metabolic capabilities, which leads to early programming for diabetes and insulin dependence. 11.1% of all births worldwide are premature, 52% of global births occur in South Asia and Sub-Saharan Africa, and more than 60% of these preterm births come from these regions. Additionally, current testing devices are invasive, painful, and expensive. Therefore, we from Team 17F had a goal to design a non-invasive system that tests glucose levels of premature babies in developing countries.
While blood is the standard for diabetes tests, extraction is invasive and therefore not applicable to our client statement. There were various body fluids that could potentially be used to test glucose levels instead because they can be collected non-invasively. We chose ISF because it is closest to blood as a biomarker for glucose content.
Our device had to have a price range of $60 to $80, an accuracy range of 95%, portability, non-invasiveness, a response time of 30 minutes or less, and accommodation for an underdeveloped hepatic system. Therefore, we landed on our current device, which consists of a wearable patch, a color sensor, and analyzation subunits.
Our device is a wearable patch that extracts ISF through reverse iontophoresis. This is a process that involves the use of electrical current to extract charged particles or molecules from the body through the skin. To extract interstitial fluid, a small current is run through the cathode and anode to push potassium ions up from the dermis layer of the skin, while a hydrogel layer provides extra protection to the skin from this current. The inlet allows glucose oxidates to be introduced with the ISF sample, and the mixer allows turbulent flow to combine the reagents together to produce hydrogen peroxide. The product of this reaction is brought up to the biosensor layer at the top of the patch through a capillary action with a glass tube, and glucose reading is available within 15 to 30 minutes from the moment of application. Our biosensor is a paper infused with horseradish peroxide and iodide. The HRP aids in the oxidation of hydrogen peroxide, so iodide is converted from a clear color to iodine, which turns the paper brown in proportional to the concentration of hydrogen peroxide. This biosensor can be used up to 60 times with 99.2% before replacement and can be removed and washed between uses through the outlet.
The color range will be detected using a color sensor pen. For this, we will be using an Arduino color sensor TCS3200. This sensor can detect a wide variety of colors based on their wavelength by using the RGB color sensor chip. It also contains 4 white LEDs that light up the object in front of it. The size of the sensor is conveniently small, allowing us to easily incorporate it into the device and enhance the device's portability. The sensor enables for direct communication to a microcontroller and is capable of high-resolution conversion of light intensity to frequency. The TCS3200 has an array of photodiodes with 4 different filters. The photodiode is simply a semiconductor device that converts light into current. The sensor has 16 photodiodes with red filter that is sensitive to red wavelength, 16 with green filter, 16 with blue filter, and 16 photodiodes without a filter. By selectively choosing the photodiode filter's readings, we are able to detect the intensity of the different colors. The sensor has a current to frequency converter that converts the photodiode's readings into a square wave with a frequency that is proportional to the light intensity of the chosen color. And this way we are able to detect the color of the test strip.
This is the code that will be uploaded onto the Arduino for display of the blood glucose level. This takes the image and extracts the average values of the red, green, blue values in the picture. This then converts these RGB values to XY coordinates on the CIE 1931 color space, which is then used to calculate the correlated color temperature. Using Wien's law, we can then calculate the wavelength, which is used as an input to the approximation model, which is used to calculate the blood glucose level. The approximation model has an R-square of 0.992, meaning it's highly accurate to the data it collects.
Our device is easy to use. The patch is placed on an area of bare skin, and after 15 to 30 minutes of extraction, the paper will have changed color. Touching the color sensor to the patch will display the glucose reading on screen. The biosensor can then be removed and washed before its next use.